Metal can pass a one-time strength test, enter service looking perfectly sound, and still break under loads that seem comfortably safe. That contradiction is metal fatigue, damage accumulated by repetition rather than one spectacular overload. It is one of engineering's least theatrical dangers, right up to the moment it becomes extremely theatrical. Engineers call the internal intensity of a load stress. When that stress rises and falls again and again, the part experiences cyclic loading. Fatigue means those cycles can consume the part's life, even when each individual load stays below the force that would break it at once. The process usually has stages. A tiny crack begins, often at the surface. It grows a little with many cycles. Then, the remaining uncracked metal becomes too small to carry the load. The final fracture may look sudden, but most of its history was quietly written beforehand. That hidden history matters wherever metal is asked to work repeatedly. Railway axles, bridges, aircraft cabins, turbine blades, offshore structures, and pipelines. The loads may come from wheels, pressure, vibration, waves, wind, or temperature. The common enemy is time counted in cycles. Shape matters as much as material. A hole, thread, shoulder, scratch, or sharp corner can create a local spike in stress, called a stress concentration. The whole component may appear lightly loaded, while one small edge is doing dangerous overtime. The 19th century railway made the problem impossible to ignore. In 1842, an axle failed near Meudon on the Versailles line, contributing to a fire and the deaths of about 60 people. Trains had created a vast experiment in repeated loading, except the specimens carried passengers. So the greatest pioneer in this field cannot merely be the first person to notice broken metal. The winner must recognize repetition as the cause, build convincing experiments, turn results into quantities designers can use, and change how working machines are judged before they fail. Deep in the Harz mining district, Wilhelm Albert faced iron hoisting chains that broke after long service. The loads were ordinary, but the consequences underground were not. His importance begins with treating those failures as a repeatable engineering problem, rather than bad luck or a mysterious weakness in one chain. Albert built a machine that repeatedly loaded chain links and reported the first known fatigue test results in 1837. That was a decisive change in method. Instead of waiting for service to supply another corpse, he made repetition happen on command and watched what survived. His experiments were close to real mining hardware, which gives them unusual practical weight, yet they remained centered on chains and the immediate mining problem. Albert proved that repeated use could destroy metal, but he did not build a broad numerical system for predicting the life of axles, beams, and other machine parts. William John McCorn Rankine approached the danger through railway axles. In 1842, he described fractures that developed progressively in service. He also warned that abrupt changes in an axle shape were dangerous and recommended generous curves where one diameter met another. That advice was remarkably modern in spirit. A smooth radius spreads stress, a sharp shoulder crowds it into a smaller region. Rankine was connecting visible geometry to hidden damage, giving railway engineers a way to improve a part before anyone could see a crack. But Rankine's contribution was primarily diagnosis and design judgment. He did not establish a sustained experimental program that mapped different stress levels against the number of cycles to failure. He showed where fatigue liked to begin, without yet supplying the full clock that measured its progress. William Fairbairn brought a different strength, scale. One of the great experimental engineers of Victorian Britain, he subjected wrought iron girders to repeated and vibratory loads. His specimens resembled the structures engineers actually wanted to build, not polished coupons chosen for laboratory convenience. Fairbairn's work asked whether long continued changes of load could weaken full-sized iron construction. That mattered to bridges, cranes, and ships, where a reassuring static calculation could miss the effect of years of movement. He helped drag fatigue out of the axle box and into structural engineering. The limitation was coherence. Large tests could reveal whether a particular girder endured, but they did not automatically produce a compact, transferable design law. Fairbairn expanded the battlefield magnificently. He did not organize every variable into a system that a railway workshop could apply part by part. James Alfred Ewing and his colleague John Humphrey then looked inside the process itself. In 1903, they observed polished metal under repeated stress and saw slip bands, fine visible lines where crystals had begun sliding along preferred planes. Those bands were not decorative scars. They marked concentrated microscopic deformation, and cracks could develop from them. Ewing and Humphrey gave fatigue a physical mechanism, replacing the vague idea that metal simply became tired with evidence of how irreversible damage accumulated inside its structure. Ewing is the strongest rival because mechanism changes understanding at the deepest level. Modern materials science still depends on watching how crystals deform and cracks grow. Yet his landmark microscopy came after engineers already had an operational framework for testing repeated loads and setting allowable stresses. He explained the hidden machinery of fatigue more clearly than he founded its design discipline. The GOAT is August Wöfler. His achievement was not one isolated observation, one clever warning, or one striking laboratory image. He joined service measurements, purpose-built machines, home test series, and practical design limits into the first durable engineering system for metal fatigue. Wöhler worked for the Prussian railways, where axle failure was an operating problem rather than an academic curiosity. In 1858, he measured the loads acting on axles during real journeys. He then calibrated those measurements, connecting what happened on the track to forces he could reproduce in controlled tests. He developed several machines for repeated bending, twisting, and direct loading. That variety mattered. Fatigue was not a property revealed by one favorite apparatus. It had to survive changes in loading method, Steffelman shape, and material before it could become dependable engineering knowledge. Across reports beginning in 1860 and culminating in 1870, Wöhler established the central fact: 90 repetitions of a stress far below a metal's one-time breaking strength could still cause fracture. He also showed that life changed systematically with stress, making failure something that could be compared and estimated rather than merely remembered. He separated two quantities that engineers still watch. Stress amplitude is how far the load swings during each cycle. Mean stress is the average level around which that swing occurs. Two parts can experience the same range of movement but have different lives because the whole cycle sits at a different average tension. Wöhler also tested details that real machines could not avoid, including changes in section and other notch-like features. He moved from simply recording fractures toward allowable working stresses and finite life design, choosing a load because the component must survive a required number of cycles, not because it passed one heroic pull. The familiar stress life graph places applied stress against cycles to failure. Wöhler published much of his evidence in tables. Later engineers plotted and extended it, and the curves eventually took his name. That distinction matters. His greatness does not depend on crediting him with every line drawn afterward, but on producing the data and logic that made the graph useful. His work earned international attention, including at the Paris exhibition of 1867. More important, railway authorities could act on it. Axles and other components could be tested under repeated loads, compared across designs, and assigned limits grounded in evidence rather than tradition alone. That is the decisive advantage over the earlier contenders. Albert made repetition experimental. Rankine exposed dangerous geometry. Fairbairn brought structural scale. Wöhler absorbed those practical questions into a program that linked service, laboratory, numbers, and design. Fatigue testing could now become an institution, not a heroic one-off investigation. Ewing still presses the hardest challenge. Wöhler could tell engineers how long specimens lasted without explaining every microscopic step inside them. Ewing and Humphrey revealed slip bands and crack origins decades later. But in this exact field, foundational fatigue engineering, mechanism completes the system. It does not precede the system Wöhler had already made operational. Wöhler's framework was not the final word. Test results scatter. Real loads vary rather than repeat neatly. Corrosion, temperature, manufacturing defects, and residual stress can alter life. Some steels show a practical endurance limit, a stress below which very long survival is possible, while many other metals do not offer such a clean threshold. Modern safety therefore adds other strategies. Safe life design retires a part before its predicted fatigue life is spent. Damage tolerance assumes a small crack may already exist, then uses fracture mechanics, the mathematics of crack growth, together with inspection intervals so the crack is found before it becomes critical. Aircraft cabins, wind turbines, bridges, trains, and pipelines now live inside that layered approach. Netzer loads, test repeated cycles, account for details, extambage, and manage remaining life. Euler deserves the title because he made time itself a design load, turning hidden repetition from an explanation after disaster into evidence engineers could use before it.